Today we are back again with our new class video, which is current electricity in this online classes. And today we'll be doing current electricity part 1 because this chapter is quite huge and we have so many topics to cover. So I'll split it into two parts. Today we'll be doing the starting part of current electricity, and then we'll go for the next part in the next lesson video. Okay, so keep your classwork ready and we'll start the current electricity now. And do have your classwork, as well as we have to draw a lot of circuit diagrams, so keep your everything ready in front of you. Okay, so let's start current electricity. So let us start current electricity with the concept of potential and EMF. Obviously we know what potential is. I mean, in lower classes we have this idea what potential is. Even we have done VOPA energy, so we understand what potential or potential energy means actually. But the EMF word, the electromotive force, is something very new. Now let me explain in a simpler way. Okay, so electricity can be obtained through certain sources. Like for our syllabus, we can think about a normal battery or cell from where we can fetch current electricity in order to see, or in order to express the basic forms of current electricity or the laws what we have in our syllabus. But when we are using these batteries or cells, they are actually built up using certain processes. Like the chemical energy can be transferred into electrical energy. Mostly this is done. Even the battery of the cell we are using nowadays in our mobile phones and in other laptops and all, they are all lithium ion, and they are also, their ionic exchange actually enable us to get the proper amount of current that is required for those devices to work. Okay, so you can understand that all these batteries, all these cells, whatever we are using, they actually transferring chemical energy into electrical energy. And while this transfer occurs, ideally we can think about, okay fine, this this transfer can give us some amount of potential, but that ideal potential is not actually what we actually get in the circuit, or when we are actually using it in a circuit, we don't get that. So EMF is basically a concept which tell us that how much energy we can transfer. Okay, so you know that the definition of potential was, it is the amount of work done to transfer a unit positive charge, and work done can be considered as to be energy. So any form of energy, suppose chemical energy is getting converted into electrical energy, so during that time also we are actually transferring one form of energy into another form. And while this transfer occurs due to the ionic exchange in the chemical reactions, ultimately the ions or the charges, they move, and that's how we can calculate the potential in current electricity. Okay, so we know potential is work done per unit charge, which is joule per coulomb, and commonly known as volt, capital V, or volt is the unit that we know. EMF is same as potential, but it is the ideal one. So EMF is designated by the letter E, is basically the ideal situation, or the energy transfer which can occur at ideal situation, and we can calculate. Suppose a battery is marked with 5 volt. So this is the EMF, but when we use it in a circuit, it may show you 4.8 volt in the circuit. This is the potential V. Okay, so that is the basic difference, so we can understand that whenever we are using a particular source to find out, to fetch current from it, the ideal situation, what it suggests, the actual value, whichever it is, that is called EMF. And whenever we are fetching current from that particular source, the amount of potential we obtain within the circuit, that is called the potential. So EMF and potential, they're a bit different. One is the ideal situation, and the second one is the actual, the amount of energy that is transferred to the circuit when we transfer one form of energy into another form of energy. And so this is the concept of EMF and potential. Now we should move into the other things like Ohm's law and the resistivity and all these parts. Okay, so let's go to the next topic. So we are starting Ohm's law. This is very important for class 10, and even for current electricity is very important. Okay, Ohm's law, actually Ohm what suggested initially is that the relation between the potential and the current, he actually devised a law which including potential and current. What he said that for a temperature and other physical properties remaining constant. This particular phrase is very important for Ohm's law. When you actually write the statement of Ohm's law, this statement of this phrase is very important. Without this, Ohm's law is basically invalid. Okay, so temperature and other physical properties remaining constant. Okay, potential current in a circuit is directly proportional to the potential applied between two ends of a conductor. Current in a conductor is directly proportional to the potential between two ends of the conductor. So what Ohm suggested, that the potential between the two ends of a conductor is directly proportional to I, and from here we actually got the concept of resistance. What we can say that V is equal to I into capital R, and this capital R is the resistance. Okay, so this is what we call the resistance of a circuit, and without resistance we cannot actually convert any other form of energy to electrical energy. This is very important fact, that if you are not attaching any resistance in a circuit, then that circuit doesn't work, because until or unless you have some point where the current electric energy will get converted into another form of energy, then only we can have the circuit get completed. Okay, we are using electricity to use it in different modes. We are like in this room, I have so many lights on, we have ACs on or fan on. All these things we are actually converting electrical energy into other form of energy, and then only these devices, all these things that we are using at home, they are all resistances connected to the circuit, and then only current will be drawn from the. If you are just connecting, not connecting any resistance, then it will be a free path. Okay, so we have to have certain devices within the circuit which is resistance, which will ultimately convert the electrical energy into other form of energy. This is the basic concept of resistance. So this is what, and from here we can write R is equal to V by I, and if I is equal to 1 ampere, then R is equal to V. So it is the resistance is the amount of potential developed when the current flowing through a conductor is 1 ampere, and that is how we can define resistance. This is the expression by which we can calculate resistance from a circuit, from a simple circuit of course, and the unit is ohm obviously, and the symbol we write is omega, which is capital Omega, and the symbol, the unit is ohm, it should be small o, sorry, so unit is ohm of the resistance. And since this is a particular situation where we are thinking that potential is directly proportional to current, keeping the temperature and other physical properties remaining constant, so resistance actually depends on a lot of things. Why Ohm told us this particular phrase, that the temperature and other physical properties remaining constant, then only this law is valid, because its resistance can vary with a lot of things. Okay, I am coming to it, but the most important fact is the resistance varies with temperature. Resistance varies with the nature of the material we are using or the nature of the substance we are using. So these things are already given in your textbook, go through it. The factors affecting the resistance of a conductor or factors affecting the resistance in an electrical circuit is very important. Okay, I will definitely, I told you already, two other factors I will do just now after this lecture goes over. I mean within this class only I will do. So the basic fact here is that resistance is the point where we can actually convert electric energy into other form of energy. See, battery is a point where we convert other form of energy into electrical energy, and that's why we have this concept between EMF and potential. But right now we are into another fact, that until and unless we have a resistance in a circuit, we cannot convert current energy or current electricity into other form of energy. And this is the expression, this is the law, the statement also I told you. So temperature is dependent, resistance is dependent on temperature, resistance is dependent on the nature of the substance we are using. Based on that, the resistance behaves differently. When we are using an alloy, it behaves differently. When we are using a metal, it behaves differently. When we are using a semiconducting material like germanium, silicon, it behaves differently. So it is very different. It is very important to know the resistance do depend on the nature of the substance. Okay. Now I'll talk about a very interesting fact about resistance. Let's check it out. So let us see how we can verify Ohm's law through a circuit. I have drawn the circuit diagram here. It's a simple one. We have one external resistance. We have one battery with certain potential. The marked EMF. We also have a rheostat. The variable resistance in order to we can change the resistance, which is connected in series. And we have one ammeter and one voltmeter, which is connected in parallel across the external resistance, and the ammeter is connected in series with the battery. We also have a key. In order to insert the rheostat, we place a key there. So this is the circuit. You should draw this circuit in your classwork, and through this circuit we can actually verify the Ohm's law. Okay, this is important because until and unless these concepts are clear to you, you won't be able to understand the basic of current electricity. It is very important, I am telling you. So this is the arrangement, and what we do is we actually change this rheostat. We change the varying resistance, and we calculate, we see the reading in the ammeter and the voltmeter. Okay, do remember while drawing this circuit, this plus minus symbols are very important because this will help you to know how voltmeter and ammeter is connected with their terminals in which side. Okay, so like in ammeter you can see that it is in the negative side with the battery, and in here it is also in the positive side with the battery. And remember one thing, that resistance, whenever you are connecting any resistance, it does not have any positive negative. Okay, it can be connected in any way you want. Resistance does not have any positive terminal or negative terminal, unlike the others do. Okay, so we have voltmeter and ammeter here, and we have this resistance. So we plot different potentials and we plot different current. One is recorded in the voltmeter, one is recorded in the ammeter with a varying resistance using a rheostat or a potential or the resistance box, whatever is available. And then we plot all these values and then we draw the graph. Okay, so ideally the graph should look like this, which is V versus I graph, and it will be a straight line according to Ohm's law, which is V proportional to I, so it will be a straight line passing through origin, and this slope definitely will give me the resistance. V by I, the slope, will give me the resistance of the particular the external resistance or whatever we are connecting. So this is fine. This we have understood, and these kind of graphs, they are called ohmic graphs. But practically what happens, you say in Ohm's law we already have this phrase that temperature and other physical properties remaining constant. But when current flows through a resistance, the temperature does not remain constant, because the when the current is flowing through the circuit, due to the electron drift, due to the flow of electron and other things, the temperature increases within the conductor. You'll see that all the electrical appliances, they get heated up after a certain amount of use. So the temperature will change, and then when the temperature is changing, we should know that the resistance depends on a particular thing. The resistance at a particular temperature is equal to resistance at 0 degree C into 1 plus alpha into change in temperature into T, you can say, where alpha is called the temperature coefficient of resistance. That means it is actually, it shows that how resistance changes with the temperature. For a normal conductor, it is the expression RT equals to R naught into 1 plus alpha T. This is the variation which is given I mean with respect to temperature how resistance varies. So here also the resistance varies, and definitely what will happen is that we won't get a curve like this. We will get a curve which is something different, and that is called non-ohmic graph, which is the ideal situation. And for non-ohmic graph we will be getting a curve, not a straight line, and in that case we'll choose certain points and we calculate the the change in potential as well as the change in current. So this will give me the change in potential, this will give me the change in current, and the resistance is given as like this. You see the difference between these two, the slope from these two different graphs are different. One is V by I directly because it was general ideal plotting of the graph, which is the ohmic graph, and this is called non-ohmic graph, where the temperature of the conductor will increase, correspondingly the resistance will increase, so the graph won't remain as a straight line governing the Ohm's law. Here the graph will be a bit different, and you see both the graphs are side by side here. Now you can understand that we have to calculate the resistance for this non-ohmic. I repeat, this is called non-ohmic. Why it is called non-ohmic? Because it is not following the Ohm's law. In other ways, practically the temperature of the conductor increases when the current passes through it, and even the other physical properties also somehow changes, and that's why we don't get this straight line. Okay, so this is it regarding the verification of Ohm's law and the ohmic and non-ohmic graphs of V versus I graphs. Those are plotted here. Okay, these are very important. These are graphical interpretations, so it's very important to know how we can actually interpret these kind of data. All right, now I'll move into other topic for the next one, which is coming up. So laws of resistance actually tells us how resistance depends on a lot of other factors involving a conductor. As I told you, in Ohm's law, temperature and other physical properties remaining constant, this phrase was there. So other physical properties remaining constant refers to a lot of things. Temperature we know already, but the other physical properties remaining constant is very important. We have already got this idea, but let us elaborate. Okay, so what is that? You see that the resistance is directly proportional to the length of the conductor. More the length, more will be the resistance, and resistance is inversely proportional to the area of the conductor. That means thicker the wire is lesser the resistance, thinner the wire, more will be the resistance. Let me tell you one simple thing. You'll see that the appliances at our home which consumes higher amount of electricity or electrical energy, like air conditioner, refrigerator, washing machines, heater, then microwaves, all these things which consumes a high amount of electrical energy. You will see the wires, the plug-in wires we use for these kind of appliances, they are quite thick because they consume more electrical energy, means they consume more amount of current, and that is the reason why if you want to pass more amount of current through a conductor, it has to be thicker, so because its resistance will be less. Okay, so knowing the consequences, we can now have these expressions together. We can actually bring a constant which is called rho, combining these two, and this symbol rho is a very specific property for a conductor, and it is called resistivity. Okay, this is very interesting fact. The resistivity of a conductor is practically dependent on a lot of factors, but rho is the constant of this kind of expression, and here we can see that rho is defined as the resistivity. The unit you can you directly calculate from here. It's basically ohm meter. Okay, because L is meter, A is meter square, so ultimately it will be ohm meter. All right, so we know what resistivity is, but we have to understand exactly the expression. For L equals to 1 unit and A equals to 1 square unit. I mean, if you imagine a cube, okay, a cube of side 1 unit and the area, area of cross section to be 1 unit. I mean, if everything is 1 meter, then this area is definitely 1 square meter. And if you assume that the current is flowing like this, I mean, from it is entering through this space and going out from there. So what you can see that if everything is 1, this is 1, the area is of cross section for these faces is 1, then everything it becomes 1, then R is equal to rho. So resistivity is defined as the amount of resistance where of a conductor having unit length and unit cross sectional area. This is the definition of resistivity. Resistivity is defined as the resistance of a conductor having unit length and unit cross sectional area, or we can imagine a cube having unit length and then the resistance between two opposite faces of that cube is also known as resistivity. Okay, so this is the thing. And again we also have another thing called conductivity. Conductivity is the reciprocal of resistivity, and it is 1 by rho, and it is actually ohm per meter. Per ohm per meter is the unit for conductivity, which is reciprocal of resistivity. Now let me tell you a few things which are theoretical, but a lot of question comes for 2 marks, 1 mark and all this. They say that what are the factors on which the resistivity of a conductor depends. Resistivity is a very unique property of the material of the conductor. Okay, the copper, it has got a standard resistivity, silver, it has got a standard resistivity, even other materials, other conductors, even the alloys, they have different resistivities, and those are constant. So resistivity depends on a lot of factors. First of all is substance, definitely. The more the substance is a conductor, the resistivity will be lesser, and because you can understand, resistivity will be more so that it can give you a more conductivity. And the substance which are insulated, they will have a very low resistivity, because it is ultimately give you an expression which is like a lot of it's dependent on the substance of the material through which we have constructed the conductor. Okay, so next is obviously the temperature, and temperature dependency of resistivity is very interesting, because of the one fact I'll show you certain graphs right now in a picture, and you'll see that resistivity varies with temperature in a different manner. For alloys, it has a different behavior. For pure metals, it has different behavior. For semiconductors, it is having a different behavior. So obviously with respect to temperature, it behaves differently. Only thing on which the resistivity does not depend, I repeat, only thing the resistivity which does not depend is the physical state or the physical dimension of the conductor. That means the length or the area. Resistance is dependent on length or area. Resistivity doesn't. Please remember this. I have seen a lot of students do this mistake, that they are asked that how resistivity of a conductor depends on the length. They write the thing what we have learned about resistance. So they mix it up, but don't mix it up. Please try to understand that resistivity is independent of the length or area of cross section or other physical dimension of the conductor. Okay, there will be certain graphs coming up now. Please watch it and understand that how resistivity and even the resistance, that means the potential versus current graph, can vary for different types of substance or different types of sources we are using, and that is very important. Like for bulb, we have a different VI graph, and also for resistivity for alloy we have different. We have pure metal, we have different. For semiconducting devices like germanium, silicon, we have different graphs. Okay, so you have to understand how these work. Graphs will come up now. So here we can see the various V versus I curves for different types of conductors, you can see, and
hopefully you can understand that all the time the graphs won't be linear like v equals to ir, so it will have curvatures, and that point of time we will be going for the non-ohmic curves that I already have shown you in the class. Okay, so please practice this graph because they can ask you to draw any one of these graphs in your board exam, so be careful about it. So here is the variation of resistivity with respect to temperature. As you can see in the graph, we have plotted the temperature in Kelvin scale, and the resistivity is in the order of 10 to the power minus 6. Okay, and we have taken an alloy nichrome, and we can see that in case of nichrome the increase in resistivity with respect to the temperature is very is not very sharp. Okay, it's increasing but very gradually, it's not going very fast, unlike conductors where resistivity increases very sharp. But here we can see that nichrome is an alloy, and you should understand, please note it down in your classwork, that alloys have a tendency to show this kind of variation with respect to temperature, that the resistivity of alloy doesn't change much with the change in temperature. Okay, please note it down.
So it's time for doing some numericals. Okay, let us do two numericals right now. The first numerical, it says that wire of 9 ohm, the resistance is 9 ohm and the length is 30 centimeter, is tripled on itself. Okay, it's tripled. They have said here it's tripled on itself. On itself. There is a big, bit of literature here. We have to understand what actually it means. It means that it is tripled on itself, means it is shortened by 1/3 of its length. So what is the new resistance that we have to find out? Okay. So here again, we can understand that this is a problem based on laws of resistance, because they have changed the length, and eventually, since the volume of the wire, suppose this is a conductor, then when we are suppose shortening it, then definitely the area of cross section will increase, and if you are stretching it, the area of cross section will decrease, since the volume of the wire or the mass of the wire is constant. So we cannot just change the length or change the area without changing the other one. Okay, so here we have to understand that the volume is constant. Okay, so since the volume is constant, so we can write that A1 L1, which is the initial volume, area into length, and that is equal to A2 L2. Okay, so it's tripled on itself. Okay, it's tripled on itself. So L2 is L1 by 3. So we can say that A1 by A2 is L2 by L1, which is 1 by 3, because L2 is 1/3 of L1, tripled on itself. So it is being moved to make it shorter. Alright, so if it is so, then what I can say, R is equal to rho L by A. So I can say that R2 by R1, where R2 is the new resistance and R1 is 9 ohm, is equal to what? Rho will get cancelled. So I'll write L2 by L1 into A1 by A2, right? So L2 by L1 is 1/3. A1 by A2 is also 1/3. So R2 is equal to 1/3 into 1/3 is 1 by 9. Okay. So if it is 1 by 9, R1 is 9. So I can say that 9 by 9. So the answer here for the new resistance is 1 ohm. Okay. You see, we have just used the normal thing, the normal formula, and that's the reason, the way we have solved the problem. And it's a pure and simple example of resistivity. Alright. Now let us do another one. Okay, here says that there are two wires of same material and same length. So they have same material and they have same length, but they have radii R1 and R2 respectively. They have different radii R1 and R2 respectively. We have to compare their resistances. This is what they want to know. Okay, so R is equal to rho L by A. Okay, and that can be further written as rho L. Since they have mentioned area, so let us write the cross-sectional area, which is pi r square. Okay, so that we can understand how we can going to relate. So we have to compare the resistance. Say R1 is to R2. So what I'm going to write, L1 by L2 into R2 square by R1 square, pi will get cancelled. L1, L2, same length. So this ratio is 1. Okay, so R2 by, R1 by R2 is finally what I'm coming. Is R2 square, small R2 square by small R1 square, the ratio. So the final answer you can write, if it is R1 is to R2, okay, it is R2 square is to R1 square, R1, R2, these are the radii of that particular wire. Okay, so this is done, but I have seen that they ask this question, they ask for the comparing the resistances, but even they sometimes ask what is the compare the resistivities. So what would be the answer? The answer would be 1 is to 1. Resistivity is 1 is to 1 because they are having the same material and they are having same length, but the radius is different, radii are different, but you know resistivity does not depend on the physical dimension of the conductor, that means length, area, all these things. Resistivity is independent on all these factors. So if they ask compare their resistivities, not resistance, then it will be 1 is to 1 because same material, same resistivity, there will be no change with respect to the change in its length or area or whatever it is. Alright, so anyways, so these are the sums that we have done and hope you have understood. We have already completed the current electricity, the part 1, the first part of your syllabus, and now I'll show you certain graphs which will tell you about the how resistivity is dependent or the how non-ohmic resistors they work at different voltage current conditions. Okay, let's check it out. This picture will pop up, and obviously I must tell you one thing, that this part is over, this section, this lesson is over, and now it's your part. You should sit and do the study the chapter from your textbook, as well as you should also do the numericals and the exercise that is there at the end of this section, this part. Okay, till then, bye bye, stay safe and stay productive.